Welcome to this explainer. Today, we're taking on a genuinely fascinating mission. We are going to decode the Earth. We'll be demystifying the invisible, highly advanced tools that scientists, governments, and urban planners use every single day to map out our world and solve some of the absolute most complex global challenges we face.
Think about this for a second. When a major storm hits, or when a massive city just keeps sprawling out, how do we actually figure out the where and the what next? How do city planners know exactly where traffic accidents are happening the most so they can fix a dangerous intersection? Or how do emergency responders know precisely which low-lying neighborhoods are at the highest risk of flooding before the storm clouds even gather? The answers to these questions don't come from guesswork. They come from incredibly powerful spatial data.
Okay, let's dive into this. Here's our roadmap for today's journey. We'll start with what is GIS? Then move to understanding remote sensing. Look at how they work together. Hit some key topics in spatial data, and finally, wrap up with real-world applications.
All right, Section 1, what is GIS, or what we like to call the smart map? We can think of this as the ultimate digital canvas. GIS literally stands for Geographic Information Systems. Now, formally, it's a system used to collect, store, analyze, and visualize data tied to specific locations on Earth. But, it goes way beyond just a static flat picture or that old-school paper map you keep in your glove box. It's an incredibly dynamic, intelligent processing environment. It evaluates relationships between totally different data sets so a municipality can figure out how to plan better traffic arteries or exactly where public funds should go to build new schools for a booming local population. It's essentially a map that thinks. And GIS builds all that profound intelligence through layers. Instead of looking at everything in just a massive, confusing jumble, the software cleanly stacks distinct categories of information right on top of each other. So, you might start with a foundational base of crisp, high-resolution satellite imagery. Then, boom, layer on the local rivers and water systems. Next, drop in the transportation network, your major highways and local streets. Add a layer detailing zoning and land use, and finally, a demographic map showing the density of the local population. By seamlessly stacking these elements, you build a comprehensive, interactive picture that reveals critical relationships you'd never see otherwise, like, say, how a proposed highway might directly intersect with an ecologically sensitive floodplain. So where exactly does all that incredible imagery that makes up the base layer of those smart maps come from? That brings us to Section 2, understanding remote sensing, or getting our data from above.
The crucial thing to grasp here is that remote sensing is the science of gathering intel about the Earth without ever actually touching it. We are capturing data from a massive distance. We do this by utilizing highly calibrated sensors loaded onto orbiting satellites, high-altitude aircraft, and low-flying drones. These sensors are specifically designed to detect and record reflected energy. Think sunlight bouncing off a dense forest canopy, or even thermal radiation emitting off a hot city street.
The sheer scale of this technology is just absolutely breathtaking. These sensors act as our unblinking eyes in the sky. Since they're constantly orbiting, measuring, and observing, the resulting images let us monitor massive, yet sometimes subtle planetary shifts over long periods of time. We can confidently track the declining health of deep rainforests, map out shifting, warming ocean currents, document the sprawling growth of urban megacities, and definitively record long-term environmental changes. We are essentially taking the continuous pulse of our entire planet. Now, just to firmly solidify the difference between these two core tools, remote sensing provides the raw data. It's the vast collection of images and the physical measurements captured by a satellite or a drone. It is the pure act of information gathering. GIS, on the flip side, is the sophisticated software system that organizes, processes, and analyzes that raw data to actually produce useful insights and navigable maps. Basically, if remote sensing is the camera snapping the picture, GIS is the brain interpreting what that photo actually means. Moving right along to Section 3, how they work together, the synergy. Because the real transformative magic happens when we witness the seamless integration of these two distinct tools. To see this handoff in action, let's say a devastating flood has just impacted a coastal region. Step 1, remote sensing springs into action. Imaging satellites passing overhead capture immediate high-resolution imagery of the newly flooded areas, showing emergency services exactly where the storm surges have spread. Then comes Step 2. That raw imagery is securely imported into our GIS software.
The platform takes that fresh visual data and cross-references it with its pre-existing layers, stuff like municipal roads, housing data, and population centers. Within minutes, it calculates exactly how many roads are currently underwater, how many homes are destroyed, and which specific communities are completely cut off from supply lines. It rapidly turns a static picture of a disaster into a targeted, actionable rescue plan. All right, on to Section 4, Key Topics in Spatial Data, Mapping the Curriculum. If you were to dive academically into this incredible technology, here is what you'd actually be studying. Notice how perfectly these foundational concepts are structured for a learner. First up, you've got GIS fundamentals. This focuses heavily on the building blocks, defining spatial data itself, understanding those complex coordinate systems that pinpoint locations across a curved Earth, and distinguishing between different map structures like point-based vector maps versus grid-based raster maps. Then you jump into remote sensing, where the focus shifts toward the mechanics of satellite imagery, understanding the physics of how various sensors capture light, and the methodologies behind accurate image interpretation. And finally, GPS and surveying. This topic is all about getting your boots on the ground to collect highly accurate physical location data in the field, which is absolutely essential for verifying or ground truthing the data we just gathered from space. As you build into more advanced territory, you move into spatial analysis. This is where you leverage the software to do complex mathematical modeling. Things like buffering, say drawing a precise 5-mile evacuation radius around a chemical spill, using data overlays, executing 3D terrain evaluations, and performing network analysis for logistics. You also learn digital image processing, which is the applied science of digitally enhancing and mathematically classifying those raw satellite images, so the software can automatically tell the difference between concrete buildings and forested areas. And ultimately, this extensive pipeline leads to web GIS and mapping. Here, analysts take all this complex spatial data and deploy it into intuitive, interactive online apps that everyday users can seamlessly click around and explore.
And that brings us to our final stop, Section 5, Real-World Applications, Transforming Society. We've examined how the data is gathered, processed, and studied. Now let's look at the ultimate so what, how these technologies are actively reshaping our modern world.
Across incredibly diverse global industries, the reliance on accurate spatial data has become absolute. In urban planning, municipal officials heavily use GIS to architect smarter, more sustainable cities and to design highly efficient public transit systems that actively reduce carbon emissions. Over in agriculture, commercial farmers harness remote sensing to continuously monitor regional crop health from space, identifying precise irrigation and fertilizer needs across thousands of acres. That spatial insight saves massive amounts of water and dramatically maximizes food yields. And regarding the environment, global scientists rely on these integrated tools to meticulously track the devastating spread of deforestation, monitor transcontinental pollution levels, and chart the undeniable, measurable progression of climate change over decades.
But the stakes get even higher when lives are immediately on the line. In disaster management, spatial data dictates the very logistics of how governments respond to catastrophic floods, sudden earthquakes, and fast-moving wildfires. These real-time maps guide emergency crews to safe access routes and help locate isolated survivors before time runs out. Furthermore, in public health, GIS is heavily utilized by epidemiologists to map out fast-moving viral disease outbreaks, tracking the geographic spread of infections. It's also used to analyze vast populations to identify healthcare deserts, regions lacking adequate hospitals, ensuring that critical medical resources, funding, and preventative care get routed precisely to the vulnerable communities that need them the absolute most.
We have journeyed all the way from the unblinking sensors orbiting in the vacuum of space down to the highly sophisticated smart maps guiding our most critical everyday decisions here on Earth. By turning raw reflections of energy into deeply layered, actionable insights, GIS and remote sensing give humanity what is essentially a spatial superpower. So I want to leave you with this final provocative thought. With the unprecedented power to observe the globe from above and deeply analyze its systems on the ground, how will these tools map our future? Think about what complex global problems